Hi everyone. In this section today we will talk about order complexity analysis. This is a very important topic when it comes to algorithms because this is a topic that teaches you what algorithm is better than the other algorithm. Okay, so while building our code we would have certain constraints that this is the memory limit of the code, this is the time limit for to execute the code, especially when you are going to do competitive programming questions. You will find such limits with every problem. So this is the topic that comes very handy and very useful in real life as well. So how do you analyze which algorithm is better? Okay, so why do we need to compare different algorithms? Let's say we have so many sorting algorithms, so which one to use? Okay, how do we compare? Okay, so comparisons are important because you need to choose which algorithm would be a better choice for a given problem. Okay, for example, you want to buy a car and there could be different types of cars available. Okay, so in one could be a racing car. Okay, another could be a maybe a normal car. Okay, maybe you want a family car. Okay, another could be a car which is more suited for a purpose of a cab. Okay, so what do? You basically go and compare different types of cars based upon the requirements. Okay, so maybe a racing car may have a higher speed, but it may also have a higher cost. Okay, family car may be in the budget and it might be a best fit for your use case. Or maybe you want to create a taxi service, then a cab would be a better choice. Okay, similarly we have different algorithms to solve a given problem. We need to choose which algorithm is better. Like we are comparing these cars based upon their, let's say, price. What would be the price in case of an algorithm? How do we compare algorithms? Okay, so running an algorithm also comes with a cost. Okay, and this cost is in the form of a space. How much extra memory this algorithm will take? If I run this algorithm, how much space it will take inside RAM? Okay, some algorithms may not take extra space, some algorithms may take extra space, but they may speed up your time as well. Okay, so we will compare which algorithm is better in terms of space and time. Okay, so ideally our first preference is we want to reduce the time taken to execute, and second priority is to reduce the space. But for certain problems we may have constraints where space is a priority and time may not be a priority. Okay, so depending upon what kind of problem statement is given to you, you will try to find out the trade-off between space and time. Now you may ask, okay, how do we compare these algorithms? Okay, so in what sense we are going to do the comparison? Will it be a absolute time? For example, if I do a sorting, one algorithm takes 1186 milliseconds, let's say, another algorithm, let's say, takes 1024 milliseconds. Okay, so are we going to note the actual time? So if we note the actual time, it is known as experimental analysis. I will also show you one example. But experimental analysis is not worth our effort because first we need to write the code, then we need to execute it, then we need to note the time taken, and then we need to plot and see which algorithm is better. Okay, so instead of doing an experiment, we will estimate the time theoretically. Okay, we will discuss, okay, if my input size is this much, then this algorithm is expected to take this much time. So what we are going to do, we are going to do theoretical analysis. Okay, I will also show you one example how we actually do experimental analysis, but that is not needed for most of the cases. Okay, so in theory what we are going to say, we are going to say both time and space are going to be some function of input. Okay, and space is also going to be a function of input. Okay, so it may happen that your time may grow linearly. It may happen that this function could be a quadratic function. Okay, it could be a quadratic function, it could be a linear function, it could be a constant function. Okay, so you can have so many different types of functions that can fit here. Okay, if you have a quadratic function, we will say that time is proportional to n square. So if your n changes from n to 10 n, let's say, then your time for let's say sorting n integers is n, is t. Then if you go from n to 10 n, your time will go from uh, like 10 square into t. Okay, so this is what is the meaning of a quadratic complexity. Okay, so if my input is, let's say, n, and it takes 1 second to execute, Then if I change my input to 10 times of my actual input, okay, then my time goes from 1 second to how much? 100 seconds. Okay, that means this quadratic time is going to grow very fast. So generally what you will see is, you will see different types of plots, time versus n. Okay, so a linear plot would look something like this. That means time is a function of n. A quadratic plot would look something like this, that it is a function of n square. Okay, and we generally depict these complexities using a notation which is known as big O notation. Okay, so what we are going to do, we will talk about big O notation, order of n square. So this basically tells us our time is some function of n square. Okay, so I can say time t of n, let's say this time is some c n square. Okay, we can have some constants plus minus, but we are not worried about that. We are worried about the biggest term. Okay, that is n square. Okay, that is in terms of n. So we generally ignore these constants. It could be 2n square, it could be 5n square, it could be 10n square. We are not worried about constants. We will write something like this, that your time follows a quadratic complexity. It is order of n square, or time is order of n, or it is log of n. Okay, or it is constant. That means irrespective of your input, your time does not change. It is going to take constant time. For example, if I say find largest element in a sorted array. Okay, in a sorted array, so in this case you don't know, you can say how, it doesn't matter how big the array is, we know the last element would always be the largest. Okay, so we can find out the largest element in constant time without iterating over the array. It will not depend upon how big the array is. So we can say it can be done in constant time, and constant complexity is written as order 1 complexity. That means your time does not change according to the input. So we can say this is nothing but O1. Okay, we may also have something very high. This is known as exponential complexity. This is 2 raised to the power n. Okay, in sub problems we will also see they follow a exponential complexity. Okay, so we are going to work note time and space as a function of the input size, and this would be the focus of this section. We will try to cover certain examples as well, and in the next lecture I will tell you how you can actually measure the runtime of the algorithm, and we will do an experimental analysis. Okay,